Good morning. The fourth class, or maybe only part of this fourth class, will be for support vector machines. What did we discuss at the end of the previous class? Support vector machines for nonlinear classification. That is what we were discussing. What was the idea to do nonlinear classification using support vector machine? Right. That is what we eventually do. That's the elegant way of doing it. So you assume that there exists some transformation and you try bringing it into a higher dimensional space where all your feature vectors there are linearly separable and do the separation. The issue there is that it is very hard to find out such transformation explicitly. Second thing is computationally pretty expensive to do all these computations in a higher dimensional space. These are the two issues are there. So then we noted certain properties that allows us to deal in the lower dimensional, in a given dimensional space itself with this problem, right? So for that, let me first also write the equation that we got. What was L of for a linear separable classification? Let's say, what was the equation that you got there? I is varying from 1 to ns minus 1 by 2 into summation I varying from 1 to ns, j varying from 1 to ns, right? Lambda I, lambda j, yi, yj, xi bar transpose times xj bar, right? This is the expression subjected to, there were a couple of constraints were there. What were subjected to? For example, lambda I should be greater than or equal to 0 anyway. Equal to, I have already eliminated it because you are considering only the support vector points. Okay, that issue is not there. That won't be 0. It would be greater. What was the other condition? Lambda I times yi, I equal to 1, 2, and 0. Is that correct? Okay, good. So for a moment, don't worry about these constraints. But look at this. What were the observations? There is, this is essentially, these are all scalars. You just have a dot product between two vectors. That is all involved in your final optimization problem to find out those classifier which has maximal margin. Correct. Now the idea is you move from this dimensional space to higher dimensional space. For that, we figured out an interesting property. Yesterday we worked it out. What that property was saying is, if I go to a higher dimensional space and do finally what I should do, even if I go to higher dimensional space, when I apply SVM, I have to do their dot product, inner product. That is equivalent to some function of this dot product. That's what we have seen. For example, yesterday it was like xi bar, xj bar whole square we have taken. That gave us same as, again it is x1, x2 only. Two vectors were there. X bar is x1, x2. And then y bar, if you call it, we went it to x1 square, x1, x2, root 2, magical number, x2 square. Three-dimensional space we went. And their dot product is equivalent to square of it in this dimensional space. It is not always true. That's where all mathematical scientists will come to our rescue. And they gave some conditions there. What was the, at least let us remember that name of that Mercier's theorem, right? Mercier's theorem tells you under certain constraints, there were a set of constraints where the dot product in the higher dimensional space can be represented as a function of dot product here in the actual original space itself. Okay. So how are we going to exploit this property? The same expression, I am going to now, instead of writing it as xi bar transpose xj bar, how do I write now? Some kernel of xi bar comma xj bar. Some kernel operation I would do, which is a nonlinear operation on xi and xj. This is what I will do. So this kernel, there are some well-defined kernels which we are going to use here and then perform this task. But what is the resultant higher dimensional space? We don't really know. That is not we are attempting yet. First thing. Okay. And is it linearly classifying it? Does it resulted in a linear classification? We don't really know. But again, let us not corner SVM too much, because we had same issues with neural networks also, right? You have hidden layers, you have output layers, you are doing it, keep on increasing it. But theoretically, there are very special instances or tailor-made instances where you really know about the distribution of the data and when it is whether it is really becoming linear or not. Okay. So it does carry drawbacks or limitations very similar to what were there for other conventional or popular methods that we have been looking at. Nevertheless, this is again a very powerful tool, because notice here the dimensionality has not exploded here. If I had written something like x1 square, x2 square, x1, x2 in similar lines, if I have gone into something else, I have to solve this problem in a very high dimensional space, that I don't have to do it. Here itself, I am able to solve this. What you do, just like you are doing in multi-neuron or multi-layer neural networks, here also what you do is you try some well-known, widely used kernels. Whichever kernel gives you good results, go ahead with that. But again, that also tells you that still there is a lot of scope for research here. How do you choose a kernel? There is no definitive answer for it. There could be some guidelines, but still there is no definitive answer on this is the kernel for this nature of data. So that's again tells you that the doors are wide open here for somebody to work or to do research here in this area. Means again, there are already some works which in the interest of time and other topics we won't be able to look at, but nevertheless, still this is an area with some good number of open problems. Okay. Say what I will do here is I will mention here some kernels, typical kernels used. That are used for it. One of them is polynomial kernels. So how is it exact? Polynomials you could use. For example, it could be, just to get rid of the subscripts, I will use two variable separate names, k of x bar comma z bar is equal to x bar transpose z bar plus 1 whole power q with q greater than 0. As we have seen, you could notice here, it's a function of inner product, nonlinear function of inner product, where you could have a polynomial out of that, very similar to square root of x1, x2 you have seen there. Okay. So this is one of, you could play with q. See, you play with some typical values of q. If that is solving your problem, be happy with that. Okay. But there is no, as I said, definitive theory that tells you, because even data is kind of, you are data dependent, not any specific distribution you are looking at. Another, hope it is still visible there. Okay, good. And another one is radial basis functions. Again, they can also come in our integrator functions also, some of these can come there, although we might not have discussed a few of them. So you would come across these things quite often in machine learning and pattern recognition. So what is this function is that here you use the kernel. What was the kernel? Exponential of norm of, okay, again minus is there, x bar minus z bar whole square divided by sigma square. This is the radial basis function, kernel for radial basis functions. Do you here by any chance see why it is a nonlinear function of inner product? Can you write it in terms of transpose and this thing? Right. So you could relate and see it as a nonlinear function again of the inner product there. Then third one is hyperbolic tangent. Tan h functions. Again, all these are applicable, even as I mentioned, I repeat that these are all applicable. You could experiment with them even in case of the integrator functions that we have seen in neural networks. So this is, for example, tan hyperbolic of beta times x bar transpose z bar plus gamma. Okay. Again, Mercier's theorem comes into play. It's not like your beta and gamma can take any values. There are set of values that you could take there. You need to verify whether that Mercier's condition is valid or not. If you want to know Mercier's theorem in more detail, all I do is to refer back to you to the textbook. Otherwise, we will keep on stuck here in SVM itself. But for now, it is okay. So if, for example, there were only if beta equal to 2 comma gamma equal to 1. So there are, for example, this way, if you fix 1, there are set of values that other can take. Okay, just like looking at some limits and doing that. Okay, these are three commonly occurring ones that you could have a look at. Now, as far as training is concerned, we are done with it now. Okay, this is how you could do during the training phase. But what about the testing phase? See, here you are doing this kernel operation and it is equivalent to taking you to some other higher dimensional space. But during testing also, you should take it to higher dimensional space and then only see in that apparently or hopefully linear space on which side of that linear hyperplane it is. Okay, there is no hyperplane, we are explicitly doing it, but that's what you have to see. So what has to be clear here is what is the final equation that you would get here. So let me write that out and then give a bit of explanation to that if required. You need to compute g of x bar, correct? So typically, had it been a linear separable case, what will you do? Or linear non-separable case also, for given x bar, you will compute g of x bar, negative or positive, you will see. Accordingly, you will assign it there, isn't it? So here on the other hand, what is means anyway our g of x bar is w bar transpose x bar plus w naught. And what is your w bar transpose now? This is equal to summation of I equal to 1 to ns lambda I. So I am writing it first for a linear case. I am writing it. Okay. In linear case, what is w bar? You all know that. Again, you can refer back the previous pages in your notebook and you should find this expression lambda I yi xi bar. Is that all? I'll get a transpose here because there is w bar transpose is there. Okay. Xi bar transpose x bar plus, just note that this w naught is just outside that. That is plus w naught. Now, can you tell me what would be the, so this is what you would, this is a linear separable case. What about nonlinear case? What would be this value? Can you tell me how you compute g of x bar here? I equal to 1 to ns lambda I yi. Help me with that. What will you do then? Very good. That's all you do. K of xi bar comma x bar plus w naught. This is nonlinear for nonlinear classification. It is exactly the same thing that you are doing in training that you are going to do here. Instead of computing xi bar transpose x bar for a given x bar, you would transpose, you do here kernel of xi bar times x bar. That is all the change. And then the story is same. You look at g of x bar negative or positive and accordingly assign it. And you would realize that with this, you will be able to get the lines which are nonlinear. This has to be very clear, support vector machines. I think we have gone into a good detail here so far. So I think that's good. Have you had this after doing a machine learning course? If you are going to say to anybody that I don't know regression, unfortunately, I haven't talked about regression so far, but we have seen it in different forms. It is not an alien for us. Okay, just that lot of terminology we haven't used. That is all. Okay, one of them happens to be this regression guy. We will see that now. Any idea? I'm sure you guys from internet courses or those who are doing other course should have heard something about this linear regression. Can you tell me about that? So far, our output y is either -1 or +1. Or if you have 3 classes, 0, 1, 2, or whatever it is, that value as such has no meaning. Okay, we were comfortable with -1 and 1 because my yi is there. I multiply it greater than or equal to 0. Constraint putting is good, and I am going in that way. But there could be a lot of instances where this yi can take any value, not just a classification is a special case of linear regression. But on the other hand, it can take any values. Okay, so those of you who had watched Andrew Ng's lectures or something else, you have watched it. So what is the example he has given for linear regression? Right, housing prediction. Very good. So what he says is, for example, number of rooms, I calls or 3-bedroom house or number of bedrooms, let's write. Otherwise, hall, how many halls are there? Number of bedrooms is one thing he says. Floor area, he says one thing. Okay, and maybe locality, right? Locality. And then you predict cost here. What is the cost here? That's the since he has started, it has turned out to be the example which we are seeing in too many places, right? You say a 3-bedroom house, and nowadays we have power cuts, so we prefer ground floor, right? Ground floor is expensive then, right? You don't worry about elevation, then ground floor is more expensive. Assume that the locality Erpedu is very good, but you want to stay in Tirupati. Okay, then what could be this? This could be, let's say, very good. You seem to have some good knowledge. Very good. 60 seems to be a good number there. Okay. Say same thing now, 2 BHK. You go to first floor. You are a big fan of IIT Tirupati, but you don't want to stay in IIT Tirupati. Outside you want to have it. So let me put Erpedu here. Should it increase or decrease? Okay, 2 BHK. So it should decrease. Very good. 35. So please give me also, if you happen to construct one, that will be a good deal. If you give me for 25 and 30, okay, 50 lakhs, let's put it there. You have all these combinations. This is what you want to, this is your feature vectors, x1, x2, x3, your y. Unlike earlier classification problem, this can take any real value. And that is all the regression. This fitting is known as the regression problem is all about. And you are doing a linear fit here. Okay. You go to now 3-dimensional space and then put these points of this cost there. I cannot write. So I will only look at I will just boil down to number of bedrooms here and the cost here I will keep. Okay. Sorry for that to disappoint you. But to draw that, it will be difficult. So you just take that, assume that you have with that it is increasing. So then you fit a line here. So now another real estate agent comes to you and tells that, well, I will give you 3 BHK here. Okay, this is in first floor. I will give you in ground floor. Locality is airpadu still. What would be the cost? Then you tell that, let my machine learning algorithm converge. I will tell you, run your algorithm, predict it, and tell the cost there. Okay, your assumption is still a linear. Otherwise, there are other methods where you do perhaps nonlinear regression. Is what needs to be done clear? Finally, have we done anything related to some setting some lines, fitting lines here when you have this data? Did we do something in this course? Okay, good. So W bar transpose into Xi bar plus W naught is equal to Yi. Correct? So such multiple Xi, Yi are there. This I is varying from 1 to n. Okay, 1 to n. You find out now the W's from that. This is not enough. Such n equations are there. Okay, then this is not exactly the linear fit where we enforce that everything should fall on the line. Okay, we have only 2 army people, so everybody will not be on the line. Only they only stand on the line. We all will be around that. So this helps us to still deal with the situation. So how do you deal with it? This will never happen. Only for a couple of guys it might happen here, but the rest are just around that. So what will you do then? How to solve this problem? This we have solved, where we enforced everybody to be on the line. Now what happened? Well, I will be close to that. Don't push me too hard to be on the line. I will be around that. Okay, then how do you solve this problem? Very good. Minimize distance between the points. Right. How do you do that? Right. Say, for example, if I tell you Xi, if I give you Xi bar, let me keep it up, because although I have taken just one, this can have, don't forget floor area and locality also. These two are also important, right? So this is Xi bar. For a given Xi bar and W bar, calculate what is the result you are getting. That has to be as close as possible to Yi. Again, just in a different combinations and different modules will come here. Again, a least square problem. That's what we are going to solve here. So what will you do? W bar transpose. Don't think that every Xi, Yi will have one W. Okay, then there is no line. Each has infinite lines then. Okay, this W bar is overall what is it that you are going to compute, right? So I could even write, if you want, J of W bar. Okay, so W bar transpose into Xi bar plus W naught. I will get it for 1 point I. The difference of it with Yi, again, he will say that I am equally at an equal distance, just I happen to be on the other side. Okay, that negative and positive should be treated equally. So how do you treat that equally? Square of that. Okay, and then what you do? This is just for 1 point. You want for all points. So summation I is varying from 1 to n. This is what you need to minimize. Again, after doing SVM, constraint optimization problem, primal dual and everything, you are again, I hope you are all masters of solving this optimization problem. Okay, don't go to primal dual, just a part of it is what we will use here. Again, for the reasons well known to you by this time, I would put half there. Okay, I would. So argument that, okay, is it minimization problem or maximization problem? Okay, I'm happy that no one told maximization, then this line will be somewhere here. Okay, because the distance is maximum. You want to minimize that. Yeah, tell me how you do that now. So J of W bar is equal to half I is varying from 1 to n W bar transpose Xi bar plus W naught minus Yi, okay, whole square. This is what I want to minimize with respect to W bar. Okay, don't do it with respect to Xi bar and all, just because you have seen another vector also there. Right. How do you do that? You need to find out W bar. Very good. Very good. So W bar new is equal to W bar old. Then what? Minus learning parameter. Mu is okay. Okay, alpha I have kept, but it's okay. Anything, whatever it is. Okay. Then what? Dou J of W bar by dou W bar. Hope you all have a DJ view that you have seen this somewhere, right? Good. Now tell me what is dou J of W bar by dou W bar. What is that? Half into, you all can see that this 2 will come here. Okay, with that desperation only we have kept half here, so it should somewhere get cancelled out. I is varying from 1 to n, then what? This will come first, right? X square, f of x whole square, 2 times fx into f dash x, correct? So 2 anyway, I brought it out. So this is W bar transpose Xi bar plus W naught minus Yi. Then what will happen? Very good. Xi or Xi bar? Xi bar. Not too bad, even if you look at it. The step you are taking is dependent on the difference, and this Xi bar is weighted by that difference, and that is what you are doing it, and your alpha is there here. Okay, then we don't have to repeat. All the possibilities that we discussed earlier would come. This incrementation I could do sample wise, and that is referred to as, so this is nothing but stochastic. I have not again used this word explicitly, but we have been discussing about it. Stochastic gradient descent. If you do this update of your W bar sample wise, that is all when you refer to it as stochastic gradient descent approach. Okay, sample wise. If that is not the case, you are using the whole stuff here, then that is a batch based gradient descent. There is some other name also, incremental gradient descent. This is also referred to as incremental gradient descent. Okay, the other one is batch gradient descent. That is all you have to do. This is the learning parameter. We already mentioned about big hop, small hop, alpha more. What are the pros and cons of each of those things we have discussed. All the theory would come here again back. Momentum term is there, where you got stuck somewhere, you want to move. So W bar some beta times your W bar old also you will add there. This is all what we discussed earlier in case of back propagation would come here. That's all. See, because That is all required to discuss about linear regression. We will try one more approach here for solving this equation. Can any of you suggest any matrix based approach to solve this problem? This is again least square problem. This is linear least squares. Okay, somewhere LLS, if you see, don't get scared. That's exactly what we are doing. Linear least square solution problem is what we are solving there. Look at the equation that is there. W bar transpose xi bar what is that? W bar transpose xi bar plus W naught, okay, equal to yi ideally. Okay, that should be equal to yi. Hope you don't mind if I drop this W naught for the reasons well known. I could absorb it into this one, correct? That also I can do. Then I could write these equations as W1 x11, let's call the first one I and the second index for the second one, plus W2 x12 and so on. Okay, L dimensional I consider. If you are very strict that my vector is L plus 1, you can put, but I'll for now keep L. WL into x1L, this is equal to y1. See, I need to find out this W, that is my goal, such that these equations are satisfied. Okay, this is one equation. There could be another sample x2 bar, which is W1 into x21 plus W2 into x22, so on, WL into x2L equal to y2. N sample points are there for me. So then W1, okay, every time don't change W. This is what you are going to find out. That is fixed for all. xn1 plus W2 xn2 plus WNL xnl equal to yn. Right? Now I am sure you will be able to suggest me how to solve this once I write it this way. See, how many variables, how many parameters are to be computed here? L parameters are to be computed. How many equations you have? N. Obviously, at least number of parameters. This will be always more in practice. Otherwise, there is no solution to that. It's like giving a point and ask you to fit a line. There are too many infinite possibilities are there. Tell me in a matrix form then. Can you represent this in a matrix and tell me? So one matrix here multiplied with that vector of x. Yeah, what should be the vector? What should be the matrix here? I'm telling you matrix. So you tell me what I should do here. So x1 bar, the whole thing will come here, this whole. Okay. But again, if you are not happy with that, I will write the whole x11, x12, x1L, x21, x22, x2L, xn1, xn2, xnl multiplied with, right, W1, W2, W. Yeah, it was, I should write here WL only. I did what I asked you not to do, but that's okay. And here, what will I get here? Right, Y1, Y2, and Yn. W11, X1. Okay, I'm getting this is just tell me the dimensionalities of this. What is the dimensionality of this? N cross L. Then what is this? L cross 1. And obviously here N cross 1. That's a good check to take a look at that. We didn't mess up too much there. Okay, then what? So I have here, let me call that as capital X here. Okay, X times W bar. Okay, good that matrix is looking bigger than your vector. is equal to y bar. How do you solve this problem? W bar. How do you get W bar out of this? X inverse. What is the dimensionality of this? N cross L. I want square. So what will you do first? See, finding out an inverse for a square matrix is convenient. How would you do? How would you get a square matrix there? Multiply both sides with, right, you multiply with X transpose X times W bar is equal to Y bar. No, yeah, here also I will get X transpose Y bar. Okay, both sides, left hand side I am multiplying it. Then what will you do? Inverse, right? So I will multiply both sides with X transpose X whole inverse. That will bring me here W bar is equal to X transpose X whole inverse times X transpose times Y bar. This is a kind of a definitive method again. It's a more stable, you could say, because you have a square matrix, then finding out the inverse of it, right? But what can you compare this with the earlier gradient descent and make comments on when we should go for what? Well, there also you could do for batch, but when will you go for that? See, what is where from the computational complexity comes here? See, this gives a more stable solution than your gradient descent, because gradient descent is a finds out a local optima there. On the other hand, this is more definitive approach. But when should you, so what is the cost that you are paying for to get that stable solution? Very good. It is the inverse that you are paying for. What is the, just take a look at the dimensionality of this. Your X is of size. What is the size of X? N cross L, X transpose, L cross N. These two will cancel out. L cross L is your X transpose X. If you are in a 1000-dimensional space, your feature vector is, you are going to find out an inverse in the 1000 by 1000. That inverse could be computationally expensive. On the contrary, take a look at your gradient descent equation. Inverse computation is much expensive than that. But again, that is good when you know roughly the solution or close to that, or else when this is manageable. Okay, if your dimensional space X transpose X computation is not that big, but it is the inverse. Again, other methods are there, right? Lot of methods are there, decomposition methods are there. We will do one of them. Of course, we might not know it because you just call INV of that matrix you will give, but lot of things are cooked inside that function. Okay, so when this is big, this can shoot up, but as long as this is something that can be handled comfortably or conveniently, you could go for this method. This is matrix based approach to solve the same equation. That's an iterative approach. Earlier one is an iterative approach until you see that changes that are happening between the earlier W bar and this is coming to some minimal changes are doing, or the line somehow you measure it. There are different ways of doing it. Until then, you iteratively go with that. This will give you, in once you have the inverse in one go, you are going to get the solution here. Clear? These two, again, the same concepts you could apply in other places also, whichever we have earlier discussed, wherever this kind of minimization problem is there. Okay. Then anyway, we discussed about linear regression. What is the other one? Logistic regression. Very good. Any idea about what is this? How is it different from linear regression? Instead of actually giving the value, if a classification problem is a simple example of your logistic regression, where after the output that you are getting here, all your activation functions The outcome of that, you could say as logistic regression. That is what we have seen, -1 and +1. That numbers as such doesn't have a meaning. But keep in mind that that's not the only way. Suppose you are interested in the probabilities. At the end of it, probability of belonging to class A, that sample, and probability of that sample belonging to class B. And on the output, you already know functions to be applied. What is our favorite function there? F of x equal to 1 by 1 plus exponential of minus x. Is it? Okay, if you want w bar transpose x bar minus y and all stuff you could write, but this is okay. Finally, this is a scalar that is fed here. What is the range of values it can take? 0 to 1 it can take. When this is infinity, right, this is 0. When this is 0, that is 1. Correct? So you could interpret it as to probabilities of this x and this also can be linked up. So just keep in mind that your outcome need not be just the classes. That is definitely one classification where, for example, 0 to 0.5, if you are getting this value, you give it to class, let's say class 1, omega 1, else you assign it to omega 2. That is what we were doing earlier. But that's not the only way. Keep in mind that you may do something with these probabilities only. You might not take any decision. You just report that. I would say with a probability of 0.3, it belongs to class 1, and 0.7, it belongs to class 2. That can be also the format of your report. That is still the logistic regression. Okay. There also the same concepts apply, and a similar logistic regression. How do you solve it? We have solved a bigger demon than this in the back propagation. We have solved it when that is there, right? So in very similar lines, the derivation follows there. You just take any standard textbook and take a look into it, and you will realize that in very similar lines, just like we did it. This is nothing new, right? If I could have even given it in your exams, should have been doing it because there was no new module there. Of course, this matrix based calculation is something new we discussed, but this also you should be able to understand based on what we discussed earlier. Okay, I'll stop here.